So this will be very reminiscent. If you remember how we did when we talked about the Lie derivative itself, which we've used here, we did a very similar calculation. This is basically the same thing. The commutator of two Lie derivatives has to do with non-integrability, in that case of the vector field itself, around a parallelogram. And in this case, it's with respect to parallel transport of a vector, but it's a very similar idea. So if we can, so what does this mean? So this means, first of all, this is a vector. We want to take its covariant derivative at O, and so that means to take the value of the vector at A and subtract its value at O. But of course we can't, as I was saying before, that doesn't really make sense, so we need to pull this back from A to O. So we need to apply TAO to this, TOA, sorry, to this object, which I'll just write as A. I'll write it like this. Okay. And now each of these is something similar. So this is TOA, but now we can ask, what is this thing? This is the change of V along the eta direction, evaluated at A. So it means the value of V at, well, that's like an epsilon. The value of V at C minus the value of V at A. So it's V at C minus V at A. Again, we want the answer to be in the tangent space of A, so we need to put here TAC, right? And similarly for this one, we will get, this means this is the eta directional derivative of V at, of V at O, so that's equal to V, so we're taking the derivative along eta here, so it's V of B minus V of O. Again, we need to pull it back from B to O, so it's TOB. Okay. So I'm not bothered with the vector index for the moment. So this is equal, of course, these are linear. These maps are linear. These parallel transport is a linear operation. It preserves sum and difference of vectors. So we can expand this out. So it's TOA TAC of V evaluated at C minus TOA of V evaluated at A minus TOB of V at B plus V of 0, okay? So that's the first thing. Now we need to just now all we have to do is anti-symmetrize this. So I want, using this anti-symmetrization symbol between C and eta. So by these brackets, I mean, as always, the skew anti-symmetrization. So what will that equal? So it says it has to be the same thing, and then we have to exchange the role of C and eta and take the difference, right? Okay. So what does it mean to exchange the role of C and eta in this picture? Well, it means to just exchange A with B. So this exchange of C with eta, it's the same thing as exchanging A with B and leaving C alone and O alone, right? In terms of the formula. So we'll get this TOA TAC times V of C. Now we have to subtract off the result of exchanging A with B. So that'll be TOB TBC times V of C. Now, if you look, these two terms have A and B occurring the same, right? If I exchange A with B, these two terms just switch. And so when I subtract off the result of exchanging A with B, I get 0. And similarly, this term doesn't have A and B in it at all. And so I get 0 here. So the leader, so therefore, that's what this anti-symmetrization is the gradient, is the commutator of these two gradients acting on B, by definition. And so it's just the difference of those two things. Now, so if I express it like this, what it's saying is it's giving us the difference between starting with the vector at C, bringing it back to O along one path, and starting with the same vector and bringing it back to O along the other path, one path going via A and one path going via B. Right? So that's what the covariant derivative is. If you like to think of it in terms of a holonomy of a loop, in other words, going, instead of saying the difference between this and this, we want to say it's just the result of going right around, say, and starting starting and ending at C. We can. The point is that to leading order. I mean, when we do this, we'll get a variation. We'll get a mismatch, and that mismatch, since it's proportional to both C and eta, will be somehow of order epsilon squared. If you think of C and eta each of themselves being of order epsilon, then that mismatch will be order of epsilon squared. If I then bring it back to O, it doesn't matter how I bring it back to O, because the difference between those will be of higher order in epsilon. You know, that it'll be itself epsilon squared times epsilon squared. So it won't. So to leading order, it doesn't really matter where we have, once we've compared these two, it doesn't matter where we look at the comparison, because we're thinking of a limit in which this parallelogram goes to 0 size. So I can also take the whole thing. I can equally well say, in fact, yeah, I can equally well say that I apply T, see, where do I want to bring it to? TCB, TBO. So I've chosen, okay, which is the inverse of this, right? So then the first term then becomes TCB, TBO, TOA, TAC, acting on D, of course, V of C. That's the only thing it can act on. And this thing, these are inverses, of course. TOB and TBO are inverses. Parallel transport from B to O and then back to B just gives you back the identity. And then these two are inverses. So I just get minus V of C. V of C. So it's just equal to 1 minus, TCB. I'll just make a shorthand notation for going along for that set of products, that product of these individual legs. And so it's that minus 1 acting on V of C, right? So either one you could think of as being the meaning of parallel transport. It's the same. I tried to convince you it's essentially the same thing, or in the limit it becomes the same thing. So either we think of it as a mismatch of two different ways of getting from O to C, or we think of it as the result of going around a loop, this parallelogram, and coming back to wherever you started, which in this way I set it up happened to be C. It could have been any of them. Okay? So let's give this a name. So what is the loop that we've done? We started at, in this case, something is I left out the C here. I said it was C, B, O, A, C. I should have put the C here. So this is a loop that starts at C, goes to A, then O, then B. So it starts at C, goes to A, then O, then B, and it comes back to C. That's this loop of parallel transport. So this commutator, if evaluated on a vector at C, let's say, is the result of starting at C, transporting that vector all the way around and coming back to C and seeing how much it's changed. So this, that's only important to keep the direction straight only for the sign. So we can define this. So we'll call this loop, let me give this a name, as just make up a name, which so I'll say exactly what I mean by this in a second. And with the convention I'm about to use, this will be a minus sign. This represents, by this symbol means the change. By that I mean the change in V if you parallel transport it around a parallelogram formed by the two vectors C and eta, and I've chosen the convention so that you go first along C and then along eta, just pure convention. And then with that convention, this is a minus sign. So that's just to write a formula. But there's one interesting thing. I mean, it's not trying to say any more than what's written right here. But there's one interesting thing in the notation, which is that, see, I've used this wedge product to represent the parallelogram. So you might know that a wedge product of two vectors, which I don't know if we ever actually defined it, so let me just define it here. That in terms of the tensor product symbol, it means it's just the anti-symmetrized tensor product. So in other words, if I introduce components, abstract industries, CA and A to B, then it's just CA, A to B minus CB, A to A. Right? So that's what I mean by the wedge product. And you might know that the wedge product of two, that in many senses, the wedge product of two vectors can be identified, can be viewed as a representation of the little element of surface that they span. In other words, if I take, this is a side comment, we won't really use this now, although it's important it is an important fact. If you take any two vectors like this, whose wedge product is the same, so for example, I could take linear combinations of them, I'll get a little element of area which will have the same area as long as the wedge product is the same and will be oriented in the same way. And furthermore, we'll have the same orientation, although this picture doesn't show the orientation. But the sign of the wedge product shows a kind of orientation. That's the orientation that I've used in this, writing this formula the way I wrote it. So we think of it as an oriented two-dimensional surface or element of surface, infinitesimal two-dimensional bit of surface. Okay, so I don't know, are people familiar? Have people run across this before? Some yes, some no. Okay. Well, it's very useful when you come to things like Stokes' theorem and integration and so on. And it's explained, it comes up all the time in connection with electromagnetic fields. In particular, this is a way of thinking of the magnetic field in 3 dimensions even, as a kind of two-form. And you can associate, if you draw pictures and think of currents running around these, you can see sort of the physical meaning in that interpretation of this wedge product, and in particular of the sign associated with it. And you can see many things like why the magnetic field is really an axial vector. If you regard it as a vector and not as a wedge product of two vectors, then it's axial and not polar. In other words, it has an extra sign under parity. All those things are sort of built into this kind of formula. But anyway, for us here, it's just a notation. So in terms of that notation, what we've shown is that the commutator of these gradients acting on V is equal to minus this thing. Now, and I remind you, although it's up there already, that we've assumed in writing this that the vector fields C and eta commute. That is, their Z bracket is 0. So from this thing, we learn several things. First of all, we look at this, we see it's the left-hand side. Sometimes I like to use this symbol for left-hand side. So it means left in some language, or a bunch of languages or something. So this left-hand side is not equal to, but what we can see from this, it's linear in Xi and eta, right? If I change this, if I replace this by a multiple of Xi, or say twice Xi and 3 times eta or whatever, or if I add C1 and C2, these by definition trivially is linear in both Xi and eta. It's also, of course, linear in V. If I rescale V or take the sum of two different V's, then I'll get the sum. So it's linear in Xi, V, and eta. And the right-hand side, this is that other thing. That's the right-hand side. That's what we see. How would you say? It's of 0 order, and it has no derivatives of V, right? Because the instruction was to take V and transport it around this curve. We don't care what the derivative of V is. We just care what V is, and that'll determine what it comes back to. So it has no. So if we put this together, we see that this expression that we've defined involves no derivatives of V. It's just a function of V alone, and it's a function of V, eta, and Xi, and it's linear in all of those. And it takes you. It's a map from the triple Xi, eta, and V to some other vector, which is this vector here, which I haven't given a name. Let's call it W. So it's a map from Xi, eta, and V to W, which is linear in each separately, linear in each of its arguments. So therefore, if you remember when we talked about tensors, any multilinear map from one set of tensors to another is itself a tensor. Okay, so that's the key. Therefore, this is given by a tensor. So this linear, these two facts together, that it's a linear algebraic function of V, with W here is a linear algebraic function of V, Xi, and eta, tells you that it must be given by a tensor. So, therefore, I can write it as, therefore, it follows that now we'll give the name of the tensor we call the curvature tensor or the Riemann tensor. So it must have the right, it's a function of Xi and eta. It's obviously by construction antisymmetric in Xi and eta. So it must take this form where, whether or not it was symmetric, it must take this form for some tensor R, A, B, C, D, and if we take into account the antisymmetry in Xi and eta, then we also learn that it's already that this tensor is antisymmetric in C and D. Okay. now this is, okay, so now we want another, so this, if you like, is the definition of the Riemann tensor, but it involves these arbitrary vector fields, C and, oh, that's because I left out B, right? I left out V, exactly. Yeah, so it has, it's this thing acting, this combination here has to act on B. So that gives the result of this gives the result of this infinitesimal loop that we were talking about. So it gives infinitesimally this loop that we just described before. But it'd be not, we don't really, I mean, it's very convenient. Often you're not contracting something with the vector fields and so on. So we just want to work, we can use this in a couple of steps to work out the commutator of the covariant derivatives themselves without worrying about contracting them with vector fields that mesh, blah, 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 just by a short calculation. So let's rewrite this grad just in terms of the commutator in question. Okay, this is just the definition of this. This is equal to, now I just expand this out. That symbol just to remind us to anti-symmetrize in Xi and eta. Then it's Xi A. So now, remember, these means operators, so we're thinking of this operating on an arbitrary tensor field on the right. So this will just be the gradient of eta dotted into the gradient of whatever stands on the right. And so, of course, it'll have two terms, one when this gradient hits eta and one where the gradient passes through and hits whatever is there. So that'll be grad A eta B times grad B plus, and then there'll be the other term, which will be eta B. Oh, let me just multiply it out. It'll be Ca eta B times grad A grad B, right? So that's just a trivial identity. But this, what am I doing? Yes. And so this, now what is this term? This term here, this we can group the terms this way. This is grad, if I write out, go back to the other notation, this is grad Xi eta B, then minus grad eta Xi B, just exchanging Xi and eta, dot grad B, plus, now we can do the anti-symmetrization. Anti-symmetrizing in Xi and eta is the same thing as anti-symmetrizing in A and B here. So it's this, which is what we're aiming to get, Gesundheit. But what is this? You've probably, if you remember, you might recognize that we already saw this combination before, right? Does anyone remember seeing this? Grad A. See? Yes, we saw it as this was our formula for the Lie derivative in terms of, so this is the Lie bracket, Xi eta B grad B plus this other term. But remember that when we set this all up, we chose two vector fields whose Lie bracket was 0. So that term isn't there, and the conclusion is that this thing, which was the left-hand side of our expression, equals this thing, which was the right-hand side of our expression. So therefore, this thing here, Ca, Cb, grad A, grad B. If we make the whole thing now act on V, then this will equal that. So in other words, the result is that, yes, maybe I should write it out explicitly. So RAB, ABCD, oops, I think I've got a different set of indices here. VB is equal to XA. I'll have to switch these to C and D now. So grad C, these are of course dummy indices, and that should have been eta, of course. D, grad C, grad D, V. I've made the whole thing to act on VA. So now we can, since C and eta are completely arbitrary, of course I can just cross them out and write an equality between what's left over. And that's sort of the most, I think, the most convenient form of a definition of the Riemann tensor. So, so that's, so the basic formula you have, I made the wrong switch. Well, okay, I'll leave it as C. Grad C, grad D, VA is equal to Riemann CDA B VB. Okay, so there's some conventions here. Not everyone uses the same convention. This is the main result, and you can take it as the definition of the Riemann tensor. Not everyone uses exactly these conventions. Some people put the indices in a different order. I think that's the only, as far as I know, they might put these two indices in a different order. They might even put the first two indices in a different order. But I think this is the most common. It's especially most common not to switch the first two indices. Anyway, so with this choice of convention, this defines the Riemann tensor. Okay. So any questions on that? So the Riemann tensor just expresses the commutator, if you like, of two covariant derivatives. And the commutator geometrically, as we saw, represents non-integrability, or this non-trivial holonomy of the covariant derivative. Oh, I mean, sorry, of parallel transport. So you might, we can also do a consistent, so that's, that completes deriving what the Riemann tensor is, but you might worry, well, maybe it looked a little fishy in some place. Is it really true that when we did this, when we compute this thing here, is it really true and acted on V? Well, where was it? This thing here, when that commutator acting on V, is it really true that it depends only on V and not on the derivatives of V? So we, just to make it seem more, less to worry about, we can do a little consistency check. So the question is, does V and its first and second derivatives really drop out? Did they really drop out? And so here's a test. I mean, here's a little check. If they really do drop out, then it must mean, it's just a consistency check now. If they really do drop out, then if we multiply V by any function f, which is 1 at the point in question, then it shouldn't affect the answer. Or another way of saying it is, if we multiply V by any function f, which needn't be a constant, the value of that function should just come out in front when we compute the commutator. So is it true that this commutator acting on Fv, and now I've got to call it C, does it equal F times the commutator acting on V? Okay. Is it clear? It's just that if it's not so, then it means that something is involved, that the gradient of V is coming in. Well, we can do this calculation easily enough. Again, just compute half the term, grad A, grad B, F, V, C, and let's just compute the left-hand side, and so that's equal to, So this left-hand side equals this. This obviously has several terms in it. But one term we compute. So we have two derivatives. They can both act on F, they can both act on V, or one can act on F and one can act on V. So the first thing will be grad A, grad V. Let me take the symmetrization away for a second. No, but then I can't. Oh well. So we need to symmetrize everything here too. So it's so one is that acting on F, multiplying by VC. Then there'll be the other term, which is the one we want, F times grad A, grad V acting on VC. And then there'll be two more terms, right? But if you look at it, this is now an anti-symmetrization in A and B. I don't have those vector fields around anymore that I dotted into the gradients, C and eta. And so I'll have two terms, and these two terms, they will differ only, I mean, in one case, the A derivative will act on F and the B on V. And in the other case, the B derivative will act on F and the A on C. So they only differ by the exchange of the indices A and B. And so we'll get zero. We'll get something symmetric, some term symmetric in A and B, which you can write down easily enough. And so therefore, under the anti-symmetrization, it gives zero. And so what's left? So that'll go away. And then this term here is what we want. This will give us F times, give us the right-hand side that we're looking for. And then, so this is the sort of right-hand side that we're looking for. And then this thing here, of course, might not be zero, except that we know this thing will just produce grad A, grad V acting on F, and the whole thing multiplying VC, right? But what's this? This we know from homework, it's just due today, I guess, is zero. So this is the statement that the connection is torsion-free, or the covariant derivative is torsion-free. So this is also zero. Okay, so then we're done. So it's just a consistent. I mean, once you've proved something, it's nice to see, well, if it's true, then it means, really this must follow, and if that follows, then it gives you more confidence that you didn't make some sort of error in the proof. Okay. So this tells us, so what we've learned is how to commute, what happens when you commute two covariant derivatives acting on a vector. But of course, in general, we'll be taking covariant derivatives of covectors and tensors and so on. So we need a formula like this that applies to covectors, and a formula like this that applies to tensors in general. So how do we get it? Well, if you think it through, we've seen all this before when we came to when we did the Lie derivative, and then even before that, or maybe it was after, depending on when you did the homework. We saw a formula like that that applies also to the Christoffel symbol. In that case, it's applying to the components of a covariant derivative in some coordinate system. In the case of Lie derivative, it's just telling you how to take, how to express the Lie derivative in terms of the covariant derivative applied to an arbitrary tensor. So we've seen similar formulas twice, and exactly the same formula, or some strictly analogous formula, also applies here. They're all for the same reason, is because they all involve basically the commutators of two things that you might call derivations, and then the commutator itself then is a derivation, and that, so those are fancy names for what's going on, but they all come from the fact that the Leibniz rule holds for tensor product. So once we know how to the commutator acts on a vector, we also know how the commutator acts on a tensor product of any vectors. And we also know how it acts on covectors because it preserves contraction. Or in this case, it's even easier to figure out how it acts on covectors because we can switch from a vector to covector by raising and lowering indices, or in this case, lowering the index using the metric. And we know that by definition, the key thing about the covariant derivative is that it preserves the metric. So the covariant derivative of the metric is 0. So you can get all those things. So let me just show, indicate what you find if you go through that reasoning. I won't do it again. And basically what's behind this, what I just said in words, is something like, if you take a commutator of two covariant derivatives and act on a vector, a tensor product, U tensor V, it's the commutator acting on U tensor V plus U tensor, this same commutator acting on V. That's in other words, this bracket, this commutator itself obeys the Leibniz rule if the individual things that are commuting obey the Leibniz rule. That's this blah 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 about derivations. So what does it tell? What does it say actually? So what does that yield now for an arbitrary tensor? Let's say with indices C, D, E, F. So each one of these indices represents a factor in a tensor product. So all we have to do is apply this Riemann tensor separately to each of those factors. That's what this formula is telling you, and that's the result. So so basically you write a bunch of terms, and you write a bunch of terms, and then for each term, exactly one of these indices is active, and it combines with the A and B indices in the way that I showed over here, although unfortunately I called them C and D here. So let's look at this first with a couple of special cases. Grad A, grad B acting on a scalar, so a tensor with no indices, just a scalar, I'll just call it phi, that's better, is equal to 0. That's the statement that it has no torsion, which we've seen. If we act on a vector, let's say, so that we know what that is. That's what we just saw. So that's a vector. If it acts on a covector, you can get it in the two ways I mentioned. But the best way, if you want to get the hang of it or just see what the pattern is, the best way is not to think of the metric being there. That'll make it look a little more confusing. But just remember the way it always goes. Remember the formula that we had for the Lie derivative, if you remember. We have to produce, so this C and D here, which is now going to be an A and B, goes along with the free indices A and B, Gesundheit again. And then we have two more indices to play with, and we have to contract them somehow with V, so let's call it VD, V sub D. And of course, the only way we can do that then is to contract, because this is a covariant index, the only way we can do that is to put the index up here. And so then the one empty slot has to be where our free index goes. So it'll be minus our DCAB acting on V. The minus sign, there's always a minus sign between the covariant and the contravariant, which is coming from the fact that if you contract a vector and a covector, you get a scalar, and the Riemann tensor has to drop out altogether, like up here. Okay, so you can always remember the sign is easy to remember because when the index moves from up to down, you get a minus sign. What's hard to remember is which is the plus and which is the minus, and in fact, different people have different conventions for it. And so on. If we apply this now to a tensor, well, I just said it again. This tensor that we had here, C, D, E, F, will get a sort of R acting on T, let's call it M, D, E, F. And there'll be a sort of M here and a C here. And then the other indices I haven't bothered with. And then there'll be then another term like this and another term. And then when we come to the covariant indices, there'll be minus terms. There'll be an RDC now with a couple of things here acting on. So now the active index is E. So it'll be T, C, D. So we have to replace the E with this dummy index, which is I call D now, not M. Let me call it M for consistency. And then F, right? So I think the pattern is clear. So you just go through the indices one by one and combine them with the Riemann tensor in such a way as to produce the right combination of indices, and you choose the sign according to whether it was covariant or contravariant. Okay? Any questions? Yeah.
The top board there, yellow, green, or whatever that is.
Yellow, maybe?
You said that the xi and eta are...
Oh, this should be an eta. I didn't bother to rewrite it.
Yeah, but to the left of that. The xi and eta are arbitrary, so you can cross it out.
Right.
They're not completely arbitrary because they have to mesh. So my question
Oh, that's true.
How numerous do they have to be for us to be able to do that?
That's a good question. So the important thing here is that we don't see whether they mesh or not because it's just their value at O, or whatever our fixed point is, that matters. So I can always extend them such that I can take any two vector fields just fixed at one point and then extend them in such a way that they mesh. That's always possible. So in the final, once we reach this point, it actually didn't matter that they meshed. But it is important. It didn't matter only because the fact that they meshed put no restriction on the values that they can have at the given point. Okay? And you can always do that because just given two vectors like this, I can just extend them. I mean, it's sort of geometrically obvious that they can always be extended. But if you don't believe, basically you're just producing a kind of two-dimensional part of a coordinate system in which xi and eta are the coordinate basis vectors. But if the geometrical picture doesn't, so yeah, this is another one of these. It's sort of obvious when you make it becomes obvious when it's obvious. So if it's not obvious, you can always go back to the formula. So what was the formula? The formula said that they meshed if and only if the commutator was 0, which says that, and what is that? That's C, I think it's written here somewhere actually, but it's C dot grad, let me write it like this, acting on eta minus eta dot grad acting on C. Now you might, well, if we want to make this completely independent of the metric, which it really is, it would be better to go into, let's choose a coordinate basis and then coordinate chart, then we'll have C alpha, partial alpha, eta beta, minus eta blah, 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 partial, exchanging the role of eta and C. Now, we asked them to be 0. That's the statement that the difference to be 0. So we asked them to be equal. That's a statement that they mesh. But you see, all this does is it gives us a restriction on the gradient of eta. So obviously I can take any vector field, given a coordinate chart, I can take any vector field eta, and I can certainly choose its the components to be constant in that coordinate chart. That's just, if that coordinate chart happened to be a momentarily inertial one, then we'd be just saying that its covariant derivative was 0. But it doesn't matter. I can take any coordinate chart, and I can choose eta I can choose this to be 0. And completely independently, I can choose this to be 0 in that coordinate chart. But since this Lie derivative is a vector, I can evaluate its components in any coordinate chart. And if there's 0 in one coordinate chart, then there's 0 in every coordinate chart, right? So I mean, in other words, it is the 0 vector. So if I can arrange, so what I'm claiming, so this is a sort of general pattern of argument that's often very useful. I want to show that I can extend, given C and eta, I can extend them in such a way that the Lie derivative vanishes. I go to a particular set of coordinates. I show that in that coordinate system, I can extend them in such a way that the Lie derivative of the one with respect to the other vanishes. But that statement is an invariant statement. It doesn't depend on, and once I've said that, it's a statement about the Lie derivative itself, and therefore it's true. And therefore, if I were to go and repeat the calculation in any other coordinate chart, I'd still get 0, even though the gradients of the individual components would no longer vanish. This difference would still vanish. So to summarize, if giving C and eta a point, I want to show I can extend them so that the Lie bracket is 0. I use a coordinate chart as an auxiliary construction, just like sometimes when you're doing Euclidean geometry, you draw extra lines in the triangle or whatever. Here we bring in a coordinate system as an auxiliary helper, and we prove that we can do the extension in that coordinate system, and then therefore we can do it. So it's both analytically obvious. There's a certain subtle trickiness perhaps in the argument, but it goes, once you get used to that mode of argument, it becomes second nature. So you can do it analytically, or you can just do it pictorially. Either way, the key thing is that puts that assumption that the Lie bracket is 0 puts no constraint on what the values can be at a given point. Okay. So we've defined the Riemann tensor. The reason I was saying before, it's important for many purposes. The most important, I suppose, is that from the Riemann tensor you can form the Ricci scalar, and that's the object that, together with the volume element formed from the metric, goes into the gravitational action. But to do that, we need to understand the Riemann tensor a little better. So in particular, it's important to understand the symmetry of the tensor, the Riemann tensor. And you actually only see its full symmetry when you view it as because if you remember when we discussed symmetry properties of tensors, they have to do with the effect of permuting indices, but it only makes sense to permute indices that are of a similar sort. So it's nice to write it as all covariant or all contravariant in talking about symmetry. And of course, this, as always, this is just the result. The tensor as we defined it had one upstairs index and 3 downstairs. So we defined the totally covariant one just by contracting with the metric. So what do we know about the symmetry of the Riemann tensor? So we already proved that it came directly out of the definition that it was skew or anti-symmetric in its last 2 indices, right? That's just because the commutator is anti-symmetric. I claim it's also symmetric in its first 2 indices. Okay. So how do we see that? The easiest way, I think, is to let it act I'm always switching between, in my notes, between A, B, and C, D. But let it act on the metric. This will be a good application. Oops. It'll be a good application of that. Yeah, there, of that formula there. So we know, of course, we know that this must equal 0 because each covariant derivative separately acting, I mean, whichever one acts on the metric, it gives 0. We know that that's equal to 0. Essentially, that's essentially how we define the covariant derivative. We just took it to be, if you remember, we showed that if this was true and if it was, what did we show, torsion-free, then it had to be the covariant derivative. So this is just a statement geometrically that parallel transport preserves lengths and angles. So that's got to be 0. But then we had a formula for this in terms of the Riemann tensor, remember, which is an example up there. So we said there should be 2 terms. Both terms will have a minus sign. So in one term, the sort of C will be the active index, and so we'll get a minus sign. We'll get the A and B coming from the derivatives here, and we'll have a C and then a D, and oh no, I can't call it D, call it M. So that's the active index C, and then D goes along for the ride. And the other term is exactly the same, RM, AB, but now D is the active index. So the C goes along for the ride, so it's GC, then the active index is M, and the dummy index is M, and the active index was D, so I have to put here D, right? So is it clear? So that's just an application of the rule we had before. So what does this mean? We don't need the minus signs anymore. So this is just the result of, this just tells us to lower the M index. So it's DCAB plus, and then this tells us it's the same, it lowers the same index, but we've swapped the roles of C and D, obviously. So we get CD, AB. So what it tells us is it tells us that it's also skew in its first 2 indices. This is another one of these things that, let me say in this case, it's sort of obvious. It's obvious. What this is telling us is that parallel transport preserves length. I mean, that's what it should be telling us because that's really where this came from. And the reason so if you think of this as a kind of curvature tensor of some connection using the language of gauge theories, well, I think the language actually came probably from here, but you might have run across it already in the case of gauge theories. This A and B has to do with that infinitesimal parallelogram that we went around. But this is telling, in the fact that parallel transport preserves length tells you that when you go around an infinitesimal parallelogram, you'll produce something that is an isometry at the tangent space where you started. In other words, you'll produce a Lorentz transformation. But since the parallelogram is an infinitesimal parallelogram, you'll produce an infinitesimal Lorentz transformation. In other words, something of the form delta AB plus some tiny, some epsilon something AB. And you might know this, or if not, you can check it, that in order for this to be preserved length, it amounts to the statement that this epsilon should be antisymmetric when you lower its indices. The statement that something is an infinitesimal Lorentz transformation is the same as the statement that it's a skew given its generator, or this epsilon thing should be a skew tensor. And that's what you're seeing. So that skewness in the first 2 indices is just telling you that the kind of connection, that the kind of holonomy this produces does preserve length. Okay, it's just a way of remembering. I mean, it's a way of sort of tying together the different ideas. So that's another symmetry. Now, that's not yet all the symmetry. Oh, there was something else I meant to say. Well, I mean, I did say it, but I meant to write it down, which is in this formula, so just note analogy with Lie derivative formulas. Remember, they looked like here I've written, this is sort of a very abstract way of saying it, but it involves a term that would have been there in correction if it had been an ordinary partial derivative, and then a correction terms which involve the gradient of c. And it's also an analogy with the formula in a coordinate system for covariant derivative. So this means many terms, and this means many terms. The terms that you see written above. Okay. That's just writing down what I said in words, just to recall the analogy that all these three sets of formulas take this similar form up to sign conventions. Oh, and in fact, yeah, the way the conventions we've chosen, here is the sign. This had the same sign, and this had the opposite sign. Unfortunately, the Lie derivative has the opposite sign with the usual conventions. Okay, so now we have one more. So this is, as many of you will know, this is not the whole story. So the Riemann tensor is symmetric in its first two indices. It's symmetric in its second two indices. But it's also symmetric when you exchange the first pair with the second pair. So like that. And it's also has another symmetry, which is the cyclic symmetry. So we need to get that too. Oof. So how will we get that? Well, we got the. Remember, we got the symmetry in the second two indices. I'm not sure we actually derived it as such, but you can get it from the fact that it corresponds to this torsion freeness, as we saw. So you can commute the two covariant derivatives acting on a scalar. If we take, using that's zero, if we commute them acting on a vector, we'll get something else, which is, well, let's leave that as. We'll get something called the Bianchi identities, but those are not just symmetry conditions. Those are differential identities on the Riemann tensor. But we can do something simpler. We can, instead of taking two, we can take three. So we can do this. We can use what is called the Jacobi identities or Jacobi identities. I'm not sure how it's supposed to be said, and act it on a scalar field, and that'll give us more symmetry of the Riemann tensor. So let me remind you about the Jacobi identity. It's just something identity for any linear operators. So we take A. It's a double commutator, right? You've probably seen it in quantum mechanics somewhere or other. So we take that and we symmetrize it in a certain way, which I'll symbolize by this. So this represents cyclic symmetry. So we cyclically permute A, B, and C. So three terms A, B, C, B, C, A, C, A, B. Add them all up, and that equals 0. So just if you expand out what these commutators are, every term cancels, right? say something. Okay, so that's a well-known identity. So let's apply this now to the case of an arbitrary scalar field and see what we get. So that's 0. So now let's write out what so this is, so 0 equals this. So let's keep these together, right? Because that's going to give us a Riemann tensor. That's what we're after. But let's expand out the first commutator so that it'll have two terms. It'll have grad A acting on grad B, commutator of grad B and grad C acting on phi, plus, or minus, sorry, the commutator of grad B and grad C acting on the gradient of phi, right? That's just what the commutator is. This thing we know is 0, which in that we see that over and over again. So Riemann tensor acting on a scalar gives 0. This is torsion-free. And so we're left with 0 equals grad B, grad, oops, but I left out the symmetry. It was a symmetrization symbol. So if we do this cyclic permutation on the commutator grad B, grad C, acting on grad A phi, we must get 0. Right? So what is this? This is a special case of that formula again. This is some covector. It happens to be the gradient of a scalar, but it's some covector, and so it's just given by the Riemann tensor again, B, C, A, D, grad D phi. Okay. I didn't put the minus sign because it's just 0. But again, now the statement, this is like the question you raised before, but it's, in this case it's more obvious. We can choose, we can make any, at a given point, we can make any covector as the gradient of some scalar. So I can cross this off, and I just get that the appropriate anti-symmetrization, or cyclic symmetrization, sorry, of A, B, C of the Riemann tensor equals 0, vanishes. And so if I write it out in full, what it's saying is grad D, A, B, C plus, and I should have said Riemann D, B, C, A plus Riemann D, C, A, B equals 0, right? So that's the other symmetry that the Riemann tensor has. Sometimes people would write it like this. Just to remind you of a notation you might have seen. Let me just pull this downstairs too. You might have seen it written like this. This suggests, people again have different normalizations for this, but what this normally suggests is total anti-symmetrization of A, B, and C. Whereas this was just cyclic permutation of A, B, and C. But because of the skewness in B and C, you can convince yourself that the cyclic permutation is the same thing. I mean, the symmetrization by cyclic permutation is the same thing as totally anti-symmetrizing it. So those are equivalent statements. So the simplest form of it is just a cyclic statement. Okay. So that's actually it. It's not obvious. I'll leave it to you as an exercise that these symmetries that we know about, I don't know how to write, try and collect them all together, then we want to say, I don't know how to say that, but I'll just call it a cyclic. You know what I mean, what the symmetry we just talked about. So those three symmetries taken together, anti-symmetric in these, and sharing cyclic symmetry, those imply all the other symmetries. So in particular, what's easy to see is I can take any three indices and the same cyclic symmetry applies to them because I can, because of the antisymmetry in the separate pairs. That's easy to see. And what's less easy to see, but I'll leave as an exercise, is that this implies the other main symmetry that you use, which is that R A, B, C, D equals R, C, D, A, B. So in other words, that's the fourth symmetry, if you like, but it's actually not independent. It just says if you swap the first pair with the second pair, it's even. If you swap within the pair, it's odd, but if you swap the pair with the pair, then it's even. And what all these symmetries, so let's just summarize. Well, I sort of summarized them all here. So the summary is, this is the first part of the summary, and the little coda for the summary is this, right? So those two, 1 and 2, are the symmetries. They're given by 1 and 2. 1 was 3 symmetries. It's interesting. Oh, this thing ran away. No, it didn't. It's interesting that there's this sort of magic set of magic tools called Young Tableau and so on, which I know as magic prescriptions, although I've never really gone through the proofs of most of them. But they're certainly worth knowing. And all of this can be summarized by the following statement. How many have actually ever worked or seen Young Tableau? 3, 4, something like that. So they represent all the possible symmetry types that a tensor can have. And they're all written in the same way. They're written as a bunch of boxes just stuck together to make a diagram, a tableau as it's called. And there are rules about which diagrams are valid. Let's not worry about them. You can't stick them together in any way. But this is one of the allowed ways of sticking them together. And it says the general state, the thing to remember about these Young Tableau is that any two indices in the same column represents an anti-symmetrization, and let's call it odd, and any two in the same row represent even. This tableau can actually be interpreted as an instruction to form a certain symmetrization operator, and what it tells you is to symmetrize in A and C, symmetrize in B and D. Having done that, anti-symmetrize in A and B, and then anti-symmetrize in C and D. And the statement is that if you apply that operator, that sequence of symmetrizations to the Riemann tensor, you'll end up with the multiple of the Riemann tensor. What you're actually doing is a projection operator on a certain subspace of symmetry types. So in this case, I'll just write what it amounts to. Remember I said anti-symmetrize in C and D after symmetrizing in A and C and symmetrizing in B and D. So this is a shorthand representation of that procedure. If we apply that to R, we get back R itself. This actually is a projection operator. If you do it twice, you'll get back the same result. Yeah.
Is it possible to write down a Young Tableau for the tensor that was on my work?
Yes. Yes. I think it's this one. That's how I got. Of course, that's what I had in mind when I made up the homework problem. Right. Yeah. Did you? Oh, I thought you had your.
Sorry.
Oh no, I thought you had. Yeah.
Can we work with this young tableau and work backwards to derive the cyclic symmetry?
Yes, you could. Right. Once you know this, you know everything about the symmetry. So that's right.
I suppose it's just group theory at that point.
Yes, I guess. I don't, as I say, it's a bit like, to me, it always appeared like just an accumulation of magic tricks. And I don't feel like I have the deeper understanding of why it all works. But it's definitely true. This statement that I've written here completely characterizes the symmetry type of the Riemann tensor. And any tensor can be decomposed into different symmetry types corresponding to the, I mean, I haven't given you the rules, but there's others, I can write some other Young tableau that look the same, but they have rearranged, permuted the indices. And then I could write other Young tableaux that aren't even of the same shape. For example, this one, and this one, and a bunch of others. And I can take each one of them gives a projection operator like this, and I can take any tensor and apply each of the projection operators, and that'll split it into its different symmetry types. And then there's a subtle ambiguity in the arrangement of so this is kind of unambiguous, just splitting it into the different empty sort of Young tableau. But each of these empty ones is the sum of filled ones, and you can fill them in different ways. So there's a kind of non-uniqueness in the way you decompose there. But that's right. What did I want to say? Another comment about can't remember now what the other comment was going to be. Oh yeah, the other comment was going to be that this thing here, when you see that sort of, my feeling about it is that is where the cyclic symmetry comes in. And since this is within this, since that 3-box tableau is within this 4-box one that represents the Riemann tensor, that's why it's cyclic. So if you were dealing with just 3 indices, not 4, and you demanded the cyclic permutation symmetry that we just saw, that summing the 3 cyclic permutations gives 0, that would put you exactly in this Young tableau, whereas this symmetry class, if you like, in 3 dimensions, there's 3 symmetry classes. These are the only 3 tableaux you can draw before you filled in any indices. And so every tensor can be split into this, this, and this. And what that means is, this is the totally, remember, odd or skew in the columns. So there's only one way to fill this in, and it just means that it's totally antisymmetric. There's only one equivalent way to fill this in, and that means it's totally symmetric. And what this is telling you is that every tensor with 3 indices can be split into 3 pieces, a totally symmetric, a totally antisymmetric, and what's left over. And what's left over is this, which has the skew symmetry. And that's not the only thing. What do I want to say? If it's totally antisymmetric, it also has the skew. No, what am I trying to say? That's right. So I think that's right. So I think this is precisely the statement that it has the cyclic symmetry, which you can see neither the totally symmetric one nor the totally antisymmetric one will have. Yeah.
So the Riemann tensor would actually have the cyclic symmetry for any 3 indices.
Any 3 indices, yeah. Right. And as I say, that you can derive fairly easily from what you see up here. Well, not quite from the. If I take the first 3, then I need also this. I need this also. Once you know that you can exchange the first pair with the second pair, then you see that it's true for any 3. and it's built into this. That's the interesting thing. And what's well, just since we're doing all this, here's complete numerology. You might ask, where does this 12 come from? There's a rule for getting the 12. It's called hooks or something like that. You go as if you were reading, and you say, how many boxes are there in the same row and column? So there's 1, 2, 3, right, in the same row and column with this. Here there's, but once you filled it, then it's gone. So you only look to the right and down, basically. So this one has 2, right? And by the same token, this has 2, and this has nothing to its right and nothing below it. So you take the product of all those, right, and you get 12. That's that 12. So, however, I don't know who dreamed this up. It also lets you count the number of components of the Riemann tensor by another one of these magic rules. You'll see that it has 20 independent components in 4 dimensions. I mean, you can get a formula for any. Okay, now better. So we want at least. Okay. So that's the symmetry. Now, the other main thing to say about the Riemann tensor is the Bianchi identities, which is a kind of differential symmetry that it has. I mean, symmetry involving derivatives. That's very important when you want to understand conservation of stress energy or energy and momentum in curved space-time. Right? That leads to a symmetry of what's called the Einstein tensor, which is just contraction of the Riemann tensor. So where are these contractions? They're coming later. Okay. So let's do that. So we just got something very useful by applying the Jacobi identity here, which is true for any 3 linear operators. Letting the linear operators be the covariant derivatives and applying it to a scalar. If we apply it to a vector, we get what's called the Bianchi identities. Okay? And then we'll have some derivatives there, as we'll see, because this holonomial, the analog of this holonomial, what's it called? Not this torsion-free condition will not apply when we have a vector. So let's take the same thing. Let's do the same thing exactly that we did before. I should mention, of course, you can verify. We haven't even written down what the components of the Riemann tensor look like in a coordinate basis, but of course, we will do that at some point. And once you have that, you can verify all these things. But these are much neater and they give much more insight into where these symmetries come from. Otherwise, they just look like some random set of equations that happens to hold. Okay. So if we do the same thing, symmetrize again the cyclic symmetry A, B, C, applied to VD, V super D, we get 0 just from the Bianchi identities. Do the same thing. This will be grad A, and now we have, so let this act, well, we know how to do this. This is Riemann B, C, D, what have I called it? M, V, M, right? And then there'll be another term where this commutator goes the other way. And so that'll be, grad A, V, D, all to be symmetrized, equals 0. This, however, we know what that is. That's equal to minus, now we have these 2 terms, depending on which is the active index, right? So if D is the active index, then it becomes Riemann, here's these BCs as always, D, M, grad A, V, M. extend this here minus that. And then because this is a covariant index, we'll get a plus, and we'll have a similar construction. BC, A is now the active index, M, grad M, V, something, D. So when we okay, so so we have three terms. When we totally anti-symmetrize in A and B, oh, maybe I should expand. No, we have to keep this for now. I guess I have to, let me write this out too. So this will give two terms. The one we're after, grad A, that's telling us something about the gradient of the Riemann tensor. And then one which we hope to go away. Okay. So the statement is when we apply a cyclic permutation symmetry to this expression, we should get 0. Now, this one, so this one, we already know. This was applying the cyclic permutation to the Riemann tensor itself, so that's what we just saw as 0. These two should be equal if we look closely. They are equal, right? And so therefore they cancel out, even without looking at worrying about the symmetry. That they're equal, they cancel out. And then what we're left is the symmetrization of this multiplied by an arbitrary vector m, and we don't even have a derivative on the m, so we don't even have to worry about whether we can choose it freely. So, oops, I forgot. So the result is, let's to make this convenient. Well, it doesn't. So the statement is A, B, C, gradient A, R, D, M, I can always lower it, equals 0. To make it look a little nicer, using what we now know about the symmetry of the Riemann tensor, I can switch this is called the Bianchi identity. But to make it a little nicer, I can switch these. I can switch the first pair of indices with the second pair of index. So B, C, D, M, let's say. And remember, because of the skewness, I can also represent this as a total anti-symmetrization if I want. So anyway, that's the statement. The statement is that if I apply a covariant derivative and pick any two of the skew indices and do the cyclic permutation with that set of three indices, I get 0. Okay. I'm not sure I said it in the clearest way, but that's sometimes you'll see it also like this, using this convention that people sometimes use of a semicolon to represent covariant derivative. So anyway, the point is, you take a gradient and then you totally anti-symmetrize on that new index that you've added together with any symmetric pair, and you must get 0. That's called the Bianchi identity. And if you contract them appropriately, so we'll come back to that, then you'll have identities on a combination of the Ricci tensor and the Ricci scalar. The Ricci tensor, of course, I haven't said what that is, but it's a contraction of the Riemann tensor. So anyway, you'll get some sort of other identity on a 2-index tensor, which is called the Einstein tensor, because it's the left-hand side of the Einstein equations. All this, by the way, has exact analogs in gauge theories. It's even I think the names are even the same. So you call this Bianchi identity. This becomes an identity on the gauge field that's produced from a vector potential. And in the case of electromagnetic field, it's something that you know, grad A F B C, again with the cyclic permutation, equals 0. So it's actually one of the Maxwell equations. As you know, if you derive F from a vector potential, one half of the Maxwell's equations become identically true, automatically true. Okay, so the main thing I wanted to get to was the geodesic. I mean, I was hoping to get to the geodesic deviation equation. I'm not sure we will. So let me just take 5 minutes and say about other interpretations of the Riemann tensor. So I think when I first started introducing the Riemann tensor, curvature idea of curvature, I think I said that possibly the most important application of the tensor itself, aside from being able to form from it a Ricci tensor and the Ricci scalar that goes into the gravitational action. But if you want to ask, what does the Riemann tensor per se do for you? It gives you this geodesic deviation equation. We won't have time to do that, but let me mention a couple of other interpretations of the Riemann tensor, sometimes called just Riem. One is related to this idea of surface elements that I just talked about. So let me write sigma for some little wedge product of two vectors representing a little surface element, little infinitesimal bit of surface. Obviously, see, this is by construction skew. This is sort of sigma A and B. It's antisymmetric in A and B. It belongs, in terms of the Young tableau, it belongs to this tableau. Since Riemann is antisymmetric, in each pair, I can apply it like this, and if I put a 1/4 here, which is a natural convention. If we assume, if we normalize this sigma so that 1/2 sigma AB equals 1, then this gives you, turns out to be, this is some curvature associated with a two-dimensional Gesundheit, some two-dimensional surface now. And this ends up being what's called the Gaussian curvature of that two surface. Remember, two-dimensional things, curvature is just given by one number, the radius of curvature. That's the Gaussian curvature. Here I'm probably thinking of I won't try to define what Gaussian curvature means for a time-like surface, but let's say it's a space-like surface, or let's say we were doing this in the Euclidean signature.
Is it just the second fundamental form?
No. Oh, in 2 dimensions, yes, you could read it. It's the second fundamental form is a tensor, but it's totally determined by a scalar in this case, which is the Gaussian curvature. Yeah, so it's just the radius. I think the statement is, well, no, let me think. No, the second fundamental form has a little more information. This is the trace of it. So I think it's the trace, yeah. It's the product of the radius. A two-dimensional surface will have if you think of it in extrinsically curvature sense, then it has two, intrinsically it just has one free parameter to represent its curvature, which is the Ricci scalar. But extrinsically, it has two radii of curvature. It could be more curved in this direction and less curved. It can curve up and and down in the other direction, like a saddle. And I think the Gaussian what's called the Gaussian curvature is, I think, the product of those two radii of curvature. with a minus sign if they're in the opposite direction. And so infinitesimally, it's a product is like a sum, which is a trace. So anyway, that's what it is, Gaussian curvature. It normalized so that the two sphere with radius 1 has Gaussian curvature of 1 is, I think, the normalization I've used. So that's one interpretation of this. Interestingly enough, it's just a curiosity, I think, but it's a kind of interesting curiosity, curious curiosity, is that this, if you think of it this way, if you think of it as what we're doing here is we're thinking of it as a quadratic form on elements of two surface. If you think of it this way, it explains to you, quote unquote, why it has all the symmetries that it has. The skewness in this, the skewness in this, that's obvious because it's meant to multiply a skew object here and a skew object here. The exchange of A, B, C, D is obvious because it's meant to be symmetric. I mean, this is a symmetric expression when I exchange sigma with sigma, which is itself. And even the cyclic symmetry is somehow built in there if you remember that these sigmas are not arbitrary two tensors, but they're these so-called simple ones that is the form of just the wedge product of two vectors. You might know that in 4 dimensions, where we are, that not every skew tensor can be written as the wedge product of two vectors. In general, it's the sum of the wedge products of vectors. So in the case of electromagnetic field, for example, if this was FAB, there's some that are called kind of pure electric, pure magnetic, or something. They're just, and even a pure radiative one, that they're just these simple wedge products. But in general, you have sums of those. Anyway. So, well, that's just a curiosity, but in some sense, it's telling you that once you know that these sigmas are simple wedge products, then it tells you you can achieve the cyclic symmetry. The parts that belong to the other Young tableau drop out. Just like you know that this is antisymmetric, the symmetric piece in A and B will drop out, and in that same sense, the thing that doesn't have the cyclic symmetry, that component of the Riemann tensor also drops out when these are simple tensors. The other I suppose I should. Any questions on this? I think I'll better. Okay, we'll start next. So the other interpretation is sort of the one that that in some sense we started with, which is that it's an obstruction to flatness. So what it means is that the Riemann tensor, I'll just write it down, the Riemann tensor equals 0 in some region, any region of M, so we call it R. No, let's not call it R, we already have R. Whatever, some region of M, if and only if that region is flat. In other words, that region looks like, modulo global considerations, it looks like it's just a subset of Minkowski space. So I guess we'll just prove that next time, and then we'll get to the geodesic deviation equation. Okay. Yeah?
Is there anything interesting we can say about this bias that exists where we can't compare angles at different places in space-time, where we compare lengths?
Many things, I think so. Yeah. What kind of thing are you looking for? What comes to mind is this Weil's unified field theory, in which he took the point of view, which in the end failed as a physical theory, although people are still trying to revive it. I mean, perennially someone tries to revive it. Maybe it'll come back, but at the moment we'd have to say that it failed in its original form, but it led directly to the notion of gauge theory, to the U1 gauge. I mean, so it led directly to the way that we think about electromagnetic field now and non-abelian gauge fields. And in fact, that's where the word gauge comes from. Gauge meaning a measurement of length. So his idea was that why should it be that angle cannot be compared from point to point, but length can be compared. That seemed to him, anyway, not right. So he wanted to make a new theory in which you could compare neither angles nor lengths, except by means of some sort of notion of parallel transport. So that you'd have, just like we introduced a new geometrical structure, which we can represent as the Christoffel symbol or the covariant derivative operator, to allow us to compare lengths and called it, to compare vectors, right, and called it parallel transport. You could, the way we introduced it, because we went back to the equivalence principle and the momentarily inertial frame, it automatically preserved length. But he said, why should, maybe the real physical one doesn't preserve length. We should be working with a more general kind of connection that preserves neither lengths, that doesn't preserve length. Although it does preserve angles. It preserves angle, but it means that we already can't compare angles except via this. And now he wanted it to not, in a sense you can say it preserves length, but only along that particular transport. Right? I mean, it should have, so in other words, length should have the same status as angle, basically. That's, I think, that was his intuition. And so, again, you can compare angles, lengths infinitesimally along a particular curve, but it won't be integrable. And if you go around some curve, and you say same length, same length, same length, same length, and you come back, you've got a different length. Just like with the synchronization, the clocks are synchronized. You come back and it's not synchronized. But, so there was a new kind of holonomy, a new kind of curvature associated with that non-integrability of length, just like the Riemann tensor is associated with non-integrability of angle. And that new thing was supposed to represent the electromagnetic field. You see, it's got see, when we wrote the Riemann tensor, it's these two things that have to do with the little transport around the little loop, those two indices. These two indices are just acting on the vector and gives an infinitesimal Lorentz transformation. If I was interested in, if I had a more general thing and traced this on these, I'd be talking about length. So in a more general situation, I'd have, if you like, a curvature for length, not just for angle. It would take the same form, but it wouldn't have these two indices because length is just a scalar, right? So it'll just have the form FCD. It'll still be skew in these two. And his idea was that was the electromagnetic field, the four-dimensional form of the electromagnetic field. And then you have Bianchi identities just like we said. You have all the other symmetry things don't enter, they become trivial. You already have all the symmetry here, but Bianchi identities enter. Again, the same story, and you get whatever I wrote there, the familiar set of Maxwell's equations. That was the proposal. But, well, it's a long story. It's not right because space-time, let's say it's not, what he was basically getting to in the end was, but I did want to say, I think I said it already, but just to finish the story. Although it wasn't right, if instead of saying length, you say phase as an electromagnetic phase, then the whole story becomes right. And this becomes to do with the non-integrability of phase rather than the non-integrability of length. And as like in the Bohm-Aharonov effect, for example, we see quantum mechanically the non-integrability of phase. So although, this was called the gauge field, or he called the invariance associated with this ambiguity in length gauge invariance, or something, I forget the exact terminology, but the word gauge was in there because gauge is a measure of length, right? So now the reason we use gauge for this phase is because it was originally meant to refer to length. That's the historical origin of that word gauge invariance. But it's wrong, right? And why is it wrong? So this is a very basic, very sort of crucial fact that different people hold different opinions on when it comes to quantum gravity. But my opinion is that it really is wrong in a very fundamental way, very deep way. It's certainly wrong in the superficial sense, because we do have a local absolute standard of length. I mean, if this was true, then you'd have no absolute standard locally of length, in the same way that we don't have an absolute local standard of angle. But we do have an absolute standard of length. You can go anywhere in the universe and you can, I don't know what's the current best standard of length. It's something using a cesium atom or something in clocks. And anyway, there's some way of reproducing the same standard of length. It used to be you had to go to Paris somewhere and there was a bar of gold. I don't know what it was. There was one bar that represented the standard of length. Even if it was that, you could, if you're careful, carry that anywhere and you'd have a standard of length. But now we have a better standard of length. So it's just not true. Space-time does know the difference between one size and another size. And then the question is that a deep fact about space-time, or is it an accident? So one point of view is that it's an accident because it's really some spontaneous image evading, that the real theory doesn't know about length. It's a conformally invariant theory. But there's some field out there, like some Higgs field associated with length, and it just settled down into some particular value, and that gives us our standard of length. So the deep structure of space-time does not know of length. That's one point of view. The other point of view is, no, this is telling us something important. The deep structure of space-time does know about length. And why should that be? The most obvious explanation is because there's an underlying discreteness in the space-time, and then that leads you off in the direction of discrete gravity theories, in particular on what I work on, causal sets. But there is this divide in point of view when it comes to pushing the theory beyond where we are now. But if you take physics as it stands, continuum physics as we know it now, without worrying about solving the problem of quantum gravity, in the physics as it stands now, there is an absolute standard of length, and we have the full metric has physical meaning, not just the conformal metric. Not only angles but lengths. The conformal metric is this. What I did was just divide out by some power of the determinant, so that when I scale g, it compensates the scale here. So that thing, let's give it a name like this, some GAB. That thing only knows about angles and not lengths. But in order to write down the equations of physics, say the Standard Model in particular, you can't get away with just this. You need the full metric. Is that what you had in mind? No.